Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about functions, but this time we'll have multiple variables instead of just a single variable. So we're actually going to be studying these types of functions with two or more variables from four different points of view, right? So first we're going to do this verbally. Let me just write them out. We're going to do it verbally, so in English, numerically, okay, why is my handwriting bad? Anyway, we'll study these functions verbally, numerically, algebraically. So here we're going to be using explicit formulas. And lastly, graphically or visually. Okay, so let's just hop right into it. Um, so here we're introduced to the idea of functions of two variables. So previously in our calculus course here, we've only talked about a function and we only have one input. Here we have to put two inputs, and this will give us a corresponding output. Okay, let's see how this works. We have a temperature T. At a point on the surface of the Earth at any given time depends on the longitude X and latitude Y of the point. So let's say this temperature T at a point on the surface of Earth. So I'm just going to say at a point on Earth. And here at any given time, we're going to say it depends on longitude X and latitude Y. So here we're looking at the coordinates of this point using its longitude X and latitude Y. And here we can think of a function of a two with two variables, right? So we say that this is the temperature of that point, which is some function where we have f of x and y, right? That's one example. So this is, here we're talking about it verbally. Another example would be, we have a volume. Let's say that's V. And this is a circular cylinder. And we're saying it depends on its radius and height, right? So here we're saying the volume depends on two things. Depends on the radius r and height h. In fact, we know that our volume, so in fact, we know that our volume is pi r squared times height because it's the area times the height. And we say that the volume is a function of r and h, right? So we can say something like our volume in terms of r and h is just equal to, well, this volume. So we don't know, we have two unknowns here, which are r, radius r, and height h. I hope that makes sense. So here, let's give a formal definition of a function of two variables. So here we say a function f of two variables. What can we say about it? It's a rule that assigns to each ordered pair of real numbers in a set D a unique real number denoted by f of x, y. How do I say this in a simple way? To each ordered pair, we're basically saying that a function f of two variables assigns x and y real numbers in a set D a unique real number denoted by a unique number, or to be more precise, a unique real number f. So what I'm saying here is I'm plugging in two values for x and y, where x and y are both real numbers. And then I get some corresponding f, which is also a real number. Right? What else can I say about it? It's similar to a function wherein I'm treating it as if it was a single variable function. Okay, maybe let's add this. So we're saying the set. Here we just named the set D. I don't know why. Could be any name though. What else? Okay, so the set D, oh, that's the reason, is the domain, right, of f. And range is the set of values that f takes on. So it would probably look something like this. So I have my function. So here I'm writing a rule. And the rule is that my x and my y are real numbers, or they belong to some set D, which is unique. Oh, no, they belong in a set D, and this gives me a real number, f of xy. Right? Okay. We don't need to dive too deep into this. I don't know how. I don't know what this is in a deeper level. But all I know is it behaves similarly like a function, a regular singular variable function. Now, we wrote it verbally. I think we did it numerically as well. Actually, no, I don't think we did. Here we say, oh, so we often write z equals f of x, y to make explicit the value taken on by f at the general point x, y. The variables x and y are independent variables, and z is the dependent variable. Compared, okay. A function of two variables is just a function whose domain is a subset of R squared, and whose range is a subset of R. When you're visualizing such a function is by means of an arrow diagram, where the domain D is represented as a subset of the xy plane, and the range is a set of numbers on a real line shown as a z-axis. For instance, if f of xy represents the temperature at the point xy in a flat metal plate with the shape of D, you can think of the z-axis as the thermometer, displaying the recorded temperatures. Okay, so I just read the whole thing, but let me try to explain it in my own. So here we say that, or we have this notation that my z is f of x, y. I plug in x and y to some function, I get a z, right? What else can we say? Well, we can say that x and y are what we call independent variables. While z depends on the value of x and y. So z is the dependent variable. Right? So a function of two variables is just a function whose domain is a subset of R squared and whose range is a subset of R. Yeah, so the domain consists of all values R squared because we're picking two variables. And then for my range, I'm picking only one. Okay, let me share a picture of what I'm looking at. I'm still trying to grasp this as well in my head. I'm trying to see like, oh, okay, it works this way. I haven't seen that yet, but hopefully I get there. Oh, there we are. I'm going to put this here. So here we're saying that, oh, uh, a function of two variables is just a function whose domain is a subset of R squared and range is a subset of R. One way of visualizing such a function is by means of an arrow diagram. So here we have these arrows that are both, they're all pointing to the right. So we have those arrows. Might actually make the picture a bit bigger. Yeah, let me do that. Okay, made the picture a bit bigger. What else can we do? So yeah, we have a bunch of arrows there where the domain D represented as a subset of XY plane. So this is the entire XY plane, right? I don't know. It's really an infinite space like that. But then the domain is only this green area where it's like a part of it. So it's not the whole XY plane, right? And the range, well, now we have a range here, is a set of numbers on a real line. So here we're talking about this one. That's a real line shown as a z-axis, right? So if I were to repeat, this is what we call the domain. This is what we call the range. So they are two completely different things. What else? For instance, if f of xy represents the temperature at the point xy, right? So we talked about the temperature problem. It's that temperature in a flat metal plate with the shape of D. So we imagine that this green thing is a flat metal plate. And then at this particular point, it has a temperature, as well as at this particular point, it has a different temperature. If we, I don't know, if we touch the metal plate, we can think of the z-axis as a thermometer displayed by recording temperatures. So if a function f is given by a formula, oh, there's another idea here, but if a function f is given by a formula and we did not specify a domain, then the domain is understood to be the set of all pairs xy. So that means the entire xy pair. So there's the idea. When we're dealing with functions of two or more variables, how do we restrict domain? Well, we actually make some sort of curve to do that, and that's the straight thing. Because in 2D, how we restrict the domain is based on this horizontal x-axis. So we could just put, okay, there's my restricted domain. And then for my y, well, I have a restricted range. I don't know, we just bound it here. And so that means this is all of the things I'm allowed to work with. I can look at the graph outside. But here it's quite different because when we're restricting the domain, we're actually making some weird looking curve here in the xy plane. And if we're dealing with range, well, we're making a new vertical axis called the z-axis. And we're plugging it there, the function. So yeah, just some interesting stuff to look at. And yeah, if it's not specified, then the domain is the set of all pairs xy for which the given expression defines a real number. So yeah, we just plug in the xy, we get an f. F is a real number. Okay, I hope that was helpful. Okay. Let's try doing some examples. So my first example here, for each function, I'm being asked to evaluate the function at a certain xy. So my x is 2, my y is 3. And then I find and sketch the domain. Okay, let's go through each of them one by one. I actually have two functions here. So my first function, let's go letter A. Here I'm given f of x, y. Let me go a bit down. And here's my function. X plus y plus 1. And I divide that by x minus 1. Well, okay, I guess now I can evaluate. So first thing I do is evaluate my f of 2/3. So I just treat it like a regular function. When I see x, I plug in a 2. When I see 3, I plug in a y. So I'm going to say f of 2 comma 3, which is, so 2 for my x, 3 for my y. That's it. Well, what did I do? Okay. There, I plug it in, then my x is a 2, 2 minus 1, 2 plus 3 is 5, plus 1 is 6, so I get square root of 6. So that's my output. Oh, it's 3 over 3 comma 2, my bad. So I messed up the question. Yeah, it's 3 comma 2. And from here, I just switch up the numbers. So I got 3 here, I got 2 and 3 here, or 3 and 2. Then I get square root of 6 over 2. I checked the answer key, I was like, why is this wrong? Okay, done. Now, that's the easy part. Now, the next part, again, was to find and sketch domain, right? So when I find my domain, I say D, okay. And here we treat it like a regular function, right? Here we say that x minus 1 cannot be 0, right? Or we could even say x plus y plus 1 could not be a negative number. So any of them would work, actually. There are two ways to do it, right? Actually, it should have been both. Okay, let me see. Also, the sketch the domain part, that one's interesting. Okay, so my domain is when I'm given some xy. Here's my rule. So I put a vertical line, and then I say my x plus y plus 1, this one, should not be a negative number. So how do I say that in math? It should be greater than or equal to 0. And the other condition was x shouldn't be 1. So those are my two conditions for my domain, right? This one cannot be a negative number. And this one cannot be a 0 or else it would be undefined. So how did I get this x not equal to 1? I just said x minus 1 should not be a 0. And I can just substitute like normal. I get x should not be equal to. That's where I got it. So that's my domain. As simple as that. Now, how do I sketch this? Well, let me try. So the way to sketch this is we can observe that the inequality x plus y plus 1 is greater than or equal to 0. And we can put my x and y, x and 1 to the other side, right? So here we're saying that, oh, x plus y plus 1 is greater than or equal to 0. This will give me my y being greater than or equal to negative x minus 1. And here I describe the points that lie on or above the line. So here we say these are points that lie on or above the line. How do I know it's on? Because it's a line. How do I know it's above? Because we still have the z value that we haven't considered. And this line is y equals negative x minus 1. While x is not equal to 1. So another thing that we saw was x equals to 1. What does this mean? It means that points uh, on the line x equals 1 must be excluded from the domain, right? So that's the idea. So if I were to do this in terms of 2D, yeah, this is only in 2D. Well, I do a xy coordinate plane. And then here I see, oh, what's my x plus y plus 1 equals 0? What's that? Well, here we see that's just this line. So y equals negative x minus 1. So it's probably like what? It goes down here maybe. That's y equals negative x minus 1. And here we say this is negative 1, right? Because we moved it down. And then here we make my y 0. So what x do I get? If we make this a 0, oh, my x is, I divide both sides by negative. So my x is negative 1 in this case. As well for my x-intercept. What else? So it's that domain. So it's all of these stuff. But then I have to exclude x equals 1, right? So I have to exclude this. That part. So we can get everything except for all of the points on this line. Now, do I bother finding the intersection? No. I don't need to. But basically, that's the domain. It's all of these stuff, all of these stuff. Okay, all of that. And then the rest. Right? Except this line. That's the domain. I'm just gonna say like what? Domain. Okay. Let's look at the other one. So my other function was in B. So this is f of x, y, which is equal to x times ln, so natural log, of y squared minus x. So here again, the easiest thing for me at least is to evaluate. So let me just do that. Here I evaluate f of 3, 2, right? So how would that look like? I change everything again, my x to 3, and everything from my y to 2. This is 4 minus 3, that's 1. 3 ln 1, that's ln 1 is 0, right? If I'm not mistaken, yeah. So this is just a 0, right? Yep. Next, I find the domain and I sketch it. So my domain here, well, basically this thing here inside my natural log, that's my only restriction. Oh, that shouldn't be a 0, because then it would have a domain error, right? Because how this function works, an ln of x, if I remembered it, I think it was like that. Where this is some y, this is some x. But here it never touches 0. So that's why, that's my only restriction. So what I'm saying is that my rule for my x and y is that my y squared minus x should be greater than 0. And so in other words, my y squared should be greater than x. If that makes sense. Or my x is less than y squared. Any of those would work. I'm just going to copy the textbook because that's what it says. Y squared is greater than x. It still works. And I think that's the only restrictions I have in this. Yeah, that's the only one. So that's my domain. And then here now I sketch. So how would this look like? Well, since my ln y squared minus x is defined only when y squared minus x is greater than 0, and that is my x is less than y squared, right? So the domain is the set of points to the left of that parabola, right? Here we say this thing. This is actually when my x is equal to y squared, right? Like the one we saw here. Oh, now that's why the textbook wanted it this way. And so my domain now is all of these, right? All of that. My x should be less than my y squared because it's less. That's why it goes to the left. If it was greater than, it would have been the other way around. I wouldn't have shaded this part, but the other part. Okay, I'm gonna stop the video here because I don't want it to be too long. I hope this gave you, or at least you guys, I hope this gave you guys a nice introduction to functions of several variables. So right now we're starting off with 2 variables. And yeah, I hope you guys stay tuned for more. See you in the next one.